In this example, we're going to develop the seismic design category for a structure to be constructed in the St. Louis, Missouri area, and then we're going to develop the response spectrum that would be used for that design. For this problem, we're going to develop a response spectrum for a site in St. Louis where the soil is characterized by a standard penetration resistance of N equals 25. And then we're going to determine the seismic design category for a risk category 2 structure to be constructed on the site. For this problem, I'm going to refer to the Applied Technology Council Hazards website, the ATC Hazards website. And when I enter in St. Louis, Missouri, I can see all the design parameters that I need for that particular site. And what I'm specifically looking for this problem are the values of S sub S, S sub 1, and T sub L. So from this, we can take away that we have an S sub S value of 0.453, an S sub 1 value of 0.16, and a T sub L of 12 seconds. The next step is to determine the site classification and then look up the site coefficients F sub A and F sub V. Since in this problem the standard penetration number has been given as 25, we know that we are in the category of a very stiff soil, or a site classification D. Referring now to table 11.4-1, and for a site classification D and a mapped value of S sub S between 0.25 and 0.50, we can find that our site coefficient F sub A is going to be between 1.6 and 1.4. Interpolation is permitted in this case, and by interpolating we can determine that F sub A should be equal to 1.438. Similarly, referring to table 11.4-2 for the site coefficient F sub V, again for a site classification D, and for an S sub 1 value between 0.1 and 0.2, we can interpolate and find that F sub V should be equal to 2.280. So given these values so far, an S sub S value of 0.453, an S sub 1 value of 0.160, a T sub L value of 12 seconds, a site classification D with site coefficients F sub A equal to 1.44 and F sub V equal to 2.28. We can next determine S sub MS as the product of F sub A and S sub S. That works out to be 0.651. And we can determine S sub M1, which is F sub V times S sub 1, and that works out to be 0.365. Next, we multiply by 2/3 in order to go from the maximum considered earthquake to the design basis earthquake. So in this case, S sub ds is equal to 0.434, and S sub d1 is equal to 0.243. Next, we can look up the seismic design category, and for a risk category 2 structure, we'll find that we are in a seismic design category C for a short, based on the short period acceleration, and that we are in a seismic design category D for the 1 second period acceleration. These seismic design categories come from tables 11.6-1 and 11.6-2. Table 11.6-1 is shown here, and this is where we look up the seismic design category based on the S sub ds value. And for a risk category 2 structure with S sub ds between 0.33 and 0.50 times G, we can see that we have a seismic design category C. Similarly, from table 11.6-2, where we have the seismic design category as a function of S sub d1 for a risk category 2 structure and a value of S sub d1 greater than 0.2, then we find that we are in a seismic design category D. Remember, we have two different seismic design categories, one based on S sub ds and a second based on S sub d1, and it's the worst of the two that governs for our particular structure. Okay. So in this case, the seismic design category would be a D. Now, if we had a risk category 4 structure, what we would find is that we would have a seismic design category D, both based on the short period acceleration S sub ds and the 1 second acceleration period S sub d1. And again, referring to table 11.6-1 for a risk category 4 structure, we can see that now the seismic design category would be a D instead of a C. And for table 11.6-2 for a risk category 4 structure, we would have a seismic design category D. So the worst of those two controls, in this case they're the same, so it's moot, but we would have a seismic design category D for both a risk category 2 and a risk category 4 structure. The next step is to develop the response spectrum for the site, and here is a blank response spectrum, or a response spectrum filled out with variables, and you can see that the plateau is marked with a spectral acceleration of S sub ds, and if we go through and fill in the values for this spectrum, we end up with a peak value of 0.434 times G. We end up with a value of 0.243 G at a period of 1 second. We end up with a minimum value at a period of 0 seconds equal to 0.174 G. And we have transitions at 0.112 seconds and 0.560 seconds. All right, so that concludes this example problem. We've determined the seismic design category for this particular structure, and we've developed a response spectrum for this particular structure on this site. Next steps, if we were to perform them, would be to develop the base shear for the structure, and then to distribute that base shear vertically and apply story forces to our structure, and then go about the design.